Once you have mastered basic sine, cosine, and tangent equations, you're ready to move on to equations involving compositions. This means that we will solve equations where the argument of the trig function is either a product or a sum. We'll begin with multiple angle equations. Here's the procedure. If the argument of a trigonometric function in an equation contains a multiple of the variable, do the following. Number 1, isolate the trigonometric function. Number 2, apply the appropriate inverse trigonometric function to isolate the argument of the trigonometric function. These two steps are the same steps that we begun with in solving basic trigonometric equations. But here's where it changes just a little bit, and this part of the procedure really requires some patience. Once you complete step 2, you're going to be tempted to solve for the variable, but we're going to postpone that till the very last step. At this point, we're going to find the smallest positive value, alpha, on the unit circle that makes the equation true. Then we'll find any other value, beta, if it exists, on the unit circle that also makes the equation true. If we're dealing with a sine or a cosine equation, we're going to make sure and add a multiple of 2 pi to each of our positive solutions to account for every possible coterminal angle with our first two solutions. And if we're dealing with a tangent equation, we're going to make sure and add a multiple of pi to find all solutions for the tangent equation. Now, once I have finished that, then step 6, finally, I can isolate the variable. Do not do this step too early. It will be tempting, but wait till the very last step to isolate the variable. Let's give this procedure a try on example 1. Find all real numbers that satisfy each equation. Remember, this is code for find every single solution in radians. Our first step in this equation is to isolate the sine function. So I'm going to subtract square root of 3 from both sides and then divide both sides by 2. We'll end up with sine of 2x equals negative square root of 3 over 2. Our trig function has been isolated. Now we're going to apply the appropriate inverse function to both sides. This is going to isolate the argument 2x. 2x equals inverse sine of negative square root of 3 over 2. Here's the part that requires a little bit of patience. Because of your experience in solving algebraic equations, the goal, of course, is always to isolate x, and we certainly want to divide by 2 at this point. But we're going to postpone that step till the very last step. Right now, I want to find 2 positive solutions on the unit circle where sine is equal to negative square root of 3 over 2. Now, remember the range of inverse sine is negative pi over 2 to pi over 2. So if I were to use my calculator to evaluate inverse sine of negative square root of 3 over 2, I'd end up with negative 60 degrees or negative pi over 3 radians. But remember, we're looking for positive solutions. So we can recognize that 5 pi over 3 is a positive angle coterminal with negative pi over 3. Sine is also negative in quadrant 3 at the location 4 pi over 3. So at this point, we can go ahead and express the solutions for the argument 2x as 4 pi over 3 plus any multiple of 2 pi to find all coterminal solutions. Also, 5 pi over 3 plus any multiple of 2 pi. And of course, k is an integer. Finally, at this step, we can isolate the variable x. We can do this by dividing both sides by 2 or multiplying both sides by a half. So I'm going to multiply every term in this first expression by a half and every term in this second expression by a half. This isolates x on the left, and as we distribute our 1/2 inside parentheses here, we're going to end up with 2 pi over 3 plus, remember I'm distributing in a half here, 2k pi times 1/2 is k pi, and 5 pi over 3 times a half gives us 5 pi over 6. Again, I'm distributing, and 1/2 times 2k pi gives us k pi. Thus, our formal solution is the set of all x such that x equals these two solutions, and it's an appropriate time to go ahead and specify that k is an element of the integers. From our expression, we can see that this equation has an infinite number of solutions, but it's always a good idea to check at least the first two solutions to make sure our expressions are set up right. So I'm going to go back to the original equation, and I'm going to type in the first answer, that is, I'm using k equals 0, the first answer in each expression, into the original equation to see if I get a balanced equation. Do notice I am in radian mode, so the calculator will evaluate this correctly. So plugging in 2 pi over 3, we can see that the equation is balanced. Now I'm going to do a shortcut here. Second entry recalls everything that I just typed in. And then I'm going to go change my angle to our second option here, 5 pi over 6. And that one balances as well. Then if you want to take it a little bit further, you can add 1 pi, you can subtract 1 pi, add 2 pi, 3 pi, and check those answers as well. But I feel pretty confident that we did this one correctly. Let's try a similar approach with example B. We have 3 tangent of pi x over 4 plus 5 equals 8. Now our first step is to isolate the trig function. So we're going to subtract 5 from both sides. Notice that's going to give me a 3 on the right side. And then I'm going to divide both sides by 3. So when we isolate our tangent function, it will be equal to 1. Now we're going to isolate the argument pi x over 4 by applying inverse tangent to the other side. Let's be patient here. We're not going to isolate x until the very last step. Let's go ahead and wrestle with our inverse tangent function. At this point, we need to find all of the locations on the unit circle where tangent is equal to 1. Now, I like this value. This one's the easy one to remember. Tangent is equal to 1 at pi over 4 radians. Now, we also know that tangent is positive down here in quadrant 3 at 5 pi over 4 radians. But recall, it's sufficient to recognize the first positive solution in the unit circle for your tangent equation, and then just add a multiple of pi to find all coterminal solutions with those two given angles. So not changing the argument, we can recognize that the argument pi x over 4 can be expressed as pi over 4 plus any multiple of pi. At this point, it's now appropriate to isolate the argument. So I'm going to multiply both sides, including both terms on the right side, by 4 over pi. That's going to isolate the variable. Then we can express the solution as x equals, let's distribute here, 4 over pi times pi over 4 is 1, and 4 over pi times k pi, notice the pi's would cancel, and I get 4k. So the solution to this equation is the set of all x such that x equals 1 plus 4k, where k is some integer. Let's go ahead and verify a couple of solutions with our calculator. Being sure that you are in radian mode, I'm going to take the first answer, x equals 1. Notice I'm using k equals 0 here. X equals 1, and I'm going to plug it into the original equation. So I have tangent of pi times 1 over 4 plus 5, and that balances the equation with 8. Now, if we take the next positive integer, k equals 1, the answer would be 1 plus 4 or 5. So again, I'm going to do the shortcut here, and I'm going to change this to pi times 5 over 4, and that one also gives me 8. Okay, now remember, you can use any integer value. So if k equals -1, the answer would be 1 minus 4 or -3. So I can also test this out in the equation by changing this to a -3, and that balances the equation as well. So we haven't checked all infinite solutions, but we have checked some representatives from our expression, and we can be confident that we solved the equation correctly. These are very similar to the basic sine, cosine, and tangent equations that we studied in the last section. The difference is we have a multiple of the angle, and we have to wait till the very end to isolate the variable. Let's practice this technique using degrees. Example 2 says find all angles in degrees that satisfy each equation. Notice we're looking for every possible solution to these trigonometric equations. So on example A, our first step is to isolate our cosine function, and we can do that by dividing both sides by -2. So cosine of 6x equals negative square root of 3 over 2. Then we're going to isolate the argument by applying inverse cosine to the other side. So we need to evaluate inverse cosine of negative square root of 3 over 2. That is, I want to find all of the angles on the unit circle whose cosine, or x-coordinate, is equal to negative square root of 3 over 2. Recall that the range of inverse cosine is 0 to 180 degrees if I'm working in degrees, and cosine is going to be negative in quadrant 2. So in quadrant 2, we can recognize that 150 degrees has a cosine of negative square root of 3 over 2. But also, we know that cosine is negative in quadrant 4, and this angle would be 210 degrees. Also, any angle coterminal with 150 or 210 would also be a solution. So I'm going to take the argument, 6x, and set it equal to 150 degrees plus any multiple of 360 degrees, or 210 degrees plus any multiple of 360 degrees. Once I have that complete solution expressed, I can finally isolate the variable by dividing all of the terms all the way across by 6. This isolates x. 150 divided by 6 is 25 degrees, and 360 divided by 6 is 60 degrees times k. 210 divided by 6 is 35 degrees, and 360 divided by 6 is 60 degrees. So I'm going to dress it up and put it in set builder notation. We have the set of all x, and we're going to specify here on the end that k has to be an integer. So this is the complete solution of the equation, but it's a good idea to double check at least the first few solutions to make sure we've done this correctly. So let's go ahead and open up our calculator and switch over into degree mode, and let's check the first two positive solutions, 25 degrees and 35 degrees. So we have -2 cosine of 6 times 25, and that should give us square root of 3. Recall that the square root of 3 is 1.732, so 25 degrees is a correct solution. We can also check our other small answer there, that's 35 degrees. And that also gives us square root of 3. Okay, now let's test out the expression with k. If k equals 1, another answer would be 25 degrees plus 60 degrees, or 80 degrees. So we can evaluate -2 cosine of 6 times 80 degrees, and well, that didn't work. I'm supposed to be doing 85, right? 25 degrees plus 60 degrees is 85 degrees. Good thing I'm checking this with my calculator. There we go. And let's try another solution from our second expression there, 35 degrees plus 60 degrees times 1. So we have -2 cosine of 6 times, and 35 degrees plus 60 degrees is 95 degrees, and that also yields the correct answer. So again, it's always a good idea to double check at least the first few solutions of your infinite set to make sure you're on the right track. All right, let's try a tangent equation. On example 2b, notice the tangent function is already isolated, so we can immediately apply inverse tangent to both sides. So 8x will be evaluated as inverse tangent of 0. So I need to find the angles on one rotation of the unit circle in degrees where tangent is equal to 0. Recall that tangent is the y-coordinate divided by the x-coordinate. Tangent is equal to 0 at 0 degrees, and it's also equal to 0 at 180 degrees. So instead of adding 180 times k to 0, it will be simplest to express this as 180 degrees times k. Finally, we can isolate our variable x by dividing both sides by 8. And we'll find out that 180 divided by 8 is 22.5 degrees times a positive integer k. So let's dress this up so it's in set builder notation. Let's specify that k is an integer, and let's put a little effort into checking this answer. My calculator is set up for degree mode, so I'm going to start with my first solution. I'm just using k equal to 1 here. Tangent of 8 times 22.5 degrees. We're looking for a 0 on the other side, and we got it. Okay, now let's suppose k equals 1. Well, we just did k equals 1. K equals 2. 22.5 times 2. That one works. Let's try a negative 1. Okay, so tangent of 8 times x, let's say 22.5 times any integer you like. Let's try negative 5. That one works as well. So again, please remember that you got to be patient, find all possible solutions, and then at your very last step, divide through to isolate the variable. And also, don't forget as you do that to divide expressions such as 2 pi k or 360k by that constant as well.